Hey, I'm Cam, and welcome to the overview of my mobile systems development project, Shooter. I have created an app that will help a player develop a consistent jump shot, boosting their confidence in their shooting ability. My role during this project was as a developer. This involved creating the UI, navigation, database connectivity, and implementing the tracking and analyzation software. I've allowed users to create an account so that the experience can be customized and their shot data can be tracked. I then provide a way for them to track the jump shot. The first time this is run, it takes 25 seconds to load, which is not ideal, but when returning to this page, will only take a few seconds. Ideally, I would have the option to record the live feed or a way to upload videos, but I did not have the time to implement this into my app. At this stage, you're able to view the live tracking of your body and a calculated angle of the interior, exterior, and predicted release angles of your shooting arm. The user is then able to view a history of their shot data, which is updated as soon as the analysis takes place. According to studies by Miller and Bartlett, a higher shooting efficiency can be achieved when the angle of release is between 44 and 52 degrees. So at this stage, I compare the angle of release to this range and give a visual representation of the result. Unfortunately, due to some issues I ran into, which will be explained later on, I was not able to develop as much as I wanted, so the usage of this data leaves a lot to be improved. To develop this app, I initially planned to use React Native due to my analysis in Milestone 1. I did, however, run into some issues that prevented me from performing the crucial identifying and tracking of the body and objects, so instead I decided to create a web app using React Native's mother library, React. According to Lay et al., this is the most popular JavaScript framework in the world, which is supported by this chart supplied by stackdiary.com as of 2021. TensorFlow is an open source machine learning and AI library that provides access to both pre-trained and custom models. These models can then be implemented into software as necessary, like image processing for security cameras and audio recognition for speech commands and much, much more. I use TensorFlow's PoseNet and Coco SSD models for pose identification and object detection, respectively. These provided me with models that have had extensive training and testing for identifying and locating key points and objects within a given image. Object detection allows me to localize and identify objects within a single image, which I would use for identifying and tracking a basketball. The model returns an array of objects which has identified with a minimum similarity level that corresponds to one of 80 objects trained within its collection. A slight oversight that I had was that the object categorized as a sports ball did not correspond to a basketball. This is why my final project was centered around more about the angles of the player rather than the tracking of a ball's motion. I performed this by using TensorFlow's pose detection model, which provided me with an API for detecting poses and body motion. This model returns an array of detected poses with 17 key points. I then set a minimum confidence level to a threshold which would allow me to identify and draw key points and the connections when they are present on the screen. I could then use these connected segments to calculate the angles of the shooter's arm. For my app, I've assumed the user is right-handed, and so track the position of the user's shoulder, elbow, and wrist to identify the current angle of release. I use Google's Firebase and authentication, as well as its Firestore database. The authentication provided by Firebase is a go-to service for many apps and websites. According to an article by careerkarma.com, companies such as Twitch TV, Duolingo, Alibaba, Trivago, and many more use Firebase for its services such as authentication. I then also decided to use the platform's database, which provided me with an all-in-one serverless backend, perfect for the limited development time I had. I used Redux for state management, which acted as my controller in my MVC design pattern. According to a study by Nelson 2020, a development team implemented Redux operations into the React code base and found that Redux simplified component creation and the pushing of props and state variables between parent and child level components. I then used Material UI and Formic libraries to access pre-made components to speed up my development. As discussed in Milestone 1, I chose MVC as my architecture pattern. The React framework provides developers with function-based components which can be built together to create larger components and pages. The rendering of these components acts as the view, and the functions and props contained within these components can be considered the model. Due to this, the need for an explicit controller is not necessary. With this being said, I used Redux, which is a state management tool. This acts as a model controller, as it allows for the state of objects to be passed between components and pages with ease, solving the issue of passing props through heavily nested areas. An example of this being used is the ability to access the current user's email, and therefore associated data on any page after the login, where this information is initialized. The Redux store wraps around the entire app, allowing for the state of this object to be used in any of my components and pages with ease. Overall, MVC went well, and if anything, I would use Redux more to make the passing of state around even easier, especially with props that I reference multiple times throughout children of parent components. I then used the idea of a proxy design pattern when loading the camera and models to display an overlaying modal view indicating that things were loading. I could have extended this by using an observer design pattern to indicate the exact progress, but I did not have the necessary information to do so. The main characteristics that I identified for the logical view is maintainability. According to Dewey et al., this involves the readability of source code, quality of documentation, and understandability of the system. I ensured that I used ESLint and Prettier on VS Code to give my code a standard format, and structured my folders to separate components. I also made tests, although this is an area I could definitely expand on, and implemented continuous integration and development actions. In terms of documentation, I ensured that my Kanban board was up to date and that I was on track by following my Gantt chart. The main characteristics of the runtime view that I identified for my mobile system were usability and performance. According to Juice et al., usability can be broken down into effectiveness, efficiency, and satisfaction, all of which can evaluate both the look of the app but also the functionality. Following the requirements from Milestone 1 to achieve a successful app, it would achieve these qualities while working on different screen sizes, browsers, which I will cover later on, and include working on a mobile. The key factor that I wanted to ensure with my app was that it would be usable on a mobile, since the basketball involves being outdoors or in a gym, places far away from a computer or a laptop. So I ensured that the camera would be able to be accessed and would allow for the same experience. I also ensured that cluttering was not prominent on my app, something that I did not have enough time to perfect on the mobile view. I did my best to follow rules such as one action, one screen, and context-orientated functionality, discussed by Juice et al. Shown in my app, each page has one function and one button that relates to the current screen, and my navigation is very simple. One thing I couldn't test extensively was that the camera view would fit on the screen without having to zoom out on mobiles, since the browser still used my webcam video, which would obviously have different dimensions to a phone camera. The next characteristic is performance. Holaru and Reddy describes this as execution time, memory usage, and battery consumption. Execution time is the time for an action to be registered and performed. In my app, actions take less than 2 seconds to perform, with the longest being the login and register. When the camera and models are being loaded, I present the user with a loading screen, which is inspired by design patterns discussed earlier. Memory use and battery consumption mostly depends on the browser being used, with browsers such as Chrome taking up more processing resources but delivering slightly better frame rate performance, and browsers such as Firefox using less resources with pretty much indifferential frame rate differences. The development process that I followed was Scrumban. This involves utilizing the visualization of workflow and limitation of work in progress from Kanban, and introduces weekly reviews and retrospective meetings provided by Scrum. This model also does not require the definitive roles set by Scrum to operate efficiently, a crucial aspect for an individual developed project such as this. This process follows iterations where I split my development into 3 main sections. On the Monday of each week, I would hold my own stand-up meeting where I would reflect on what went well, what I had developed in the past week, what I was planning to work on during that week, and spend time looking into how to solve any issues I had. It was here that I would look at my Kanban board, update it as necessary, and look to the next feature I was going to develop. This process worked very well, and I was able to review and delegate upcoming tasks and prioritize the order based on importance. Within my Kanban board, each column had a restriction on the number of current tasks. I had a retrospective meeting on the last day of each iteration. It was here that I would review my current progress. It was on my second retrospective meeting that I decided to stop spending time on attempting to fix the TensorFlow issue, and instead dedicated myself from starting from scratch with a React web app. This shows how crucial and agile process was to this project, as I was able to change the requirements of my entire system. This process worked perfectly for my project as it supplied me with the information and motivation to keep on track and constantly evaluate my current position within the iterations and overall project progression. The key physical view characteristic that I identified was compatibility. With my initial idea being a cross-platform app, my requirements would be device, version, and performance compatibility, stored from Murky and Roo. I'd set a minimum software version of Android of 8.2 and iOS of 11. With the change to React, instead my requirements revolved around the version of the browser being used. Fortunately, this is controlled by the device's operating system, which would allow for the device to only download versions that are compatible with the current OS version. In terms of compatibility with my video recognition, according to the official TensorFlow website, TensorFlow will automatically choose the best backend for the given environment. This means that the devices and browsers that can utilize things such as WebGL, which utilizes the device's GPU to perform up to 100 times faster operations, will do so, and if not, will then use WebAssembly or the vanilla JavaScript CPU.